you guys to go get through. We'll take a look at a bunch of stuff that I wanted you guys to have gotten through. Some stuff that we did together. And then we'll move on to the new stuff today. You guys got a chance to look at this in class. Did we get this thing done? Some did, some did not. Okay. This is I'll go through the answers. What you could have done for each one of these questions. If you didn't have a chance to go through it, again, you can do that on your. Assuming you have a computer at home, do that on your own time. Forces being balanced. Again, if you're taking a look at the PhET simulation, you could have had a free body diagram looks like this. A scenario where they're unbalanced to either one of these is something you could have created for the next chunk. And then I got you to play around with specific things. You went to the motion tab, or you were to go to the motion tab and play around with the simulation. These are the results you should have ended up with. As soon as the force was no longer applied, the speed of the skateboard or the refrigerator should have remained constant. The speed would have remained constant because the forces were balanced. Gravity and normal force were acting on the skateboard refrigerator combo. And will the thing ever stop moving? In that simulation, no. In real life, yeah, because there's friction in the bearings and air resistance. So this is what, if you would have worked through it, these are responses you could have given to any of those kinds of, or to any of these questions. On the next page, these are responses you could have given. What happens to the speed of the skateboard when the force is continuously applied? It goes up as long as there's a force acting. The thing should be accelerating, and the reason for it is because those forces are unbalanced. You would have ended up with something that looks like that. And then you added friction in step 2, in part 2. So the presence of friction slows the things down, makes it harder to move. This is the responses you could have given it. Friction and applied would have been balanced before the object starts moving, and you would have increased the applied force. Eventually, what you should have noticed is that once the object starts moving, friction and the applied force are no longer balanced. They're now unbalanced. And the size of the friction force actually drops. So it doesn't stay what it was. Did you guys all get a chance to see this? Did you guys get a chance to see this? Liam, you said you guys had time to work through this. Did you see this happen?
Yeah.
You made it. Yeah. So I mean, Sarah, you said you didn't have a chance to look at this. I want to make sure you guys all see this. It's something that we are going to look at when we talk about friction, but I do want you to see it here. So we're going to open the friction one. So you've got setup looks like this. All the boxes in the upper right corner are checked. Forces, sum of forces, values, mass, and speed. So we've got everything here. Play around so you know it works. We want this thing to, so we're going to start applying a force. And then you can see as it's growing, and I can't remember what the number was, but as the force is growing, the applied force is growing, you can see that friction is growing in response to it. And now, again, it's a simulation, so the temptation is to say to yourself, well, it's just a simulation. This isn't how it works in real life. But the people who design this thing make an effort to have it at least approximate real life as much as you're gonna see it. So we can continue to crank the force up here, and you can see it. The friction force is going to continue to grow to match the applied force. This is what happens for an object that you're pushing on that's not moving. The reason you're pushing on it, so you have given it an applied force, for it to not be sliding means the friction force has to be the same. It can't be bigger, because if this all of a sudden was bigger, that means you pushing on it would fling the box back at you, which wouldn't work. So friction has to match your applied force, and eventually, I think it's right around 120, I think. if I remember this thing properly, is 126. Okay. You're going to see here it matches. If I hit 126, this is 125 and 125. Now this is 126. We've increased our applied force by 1, but if you notice what happened here, the friction force dropped to 94. That is, let me look at something here. We are not going to talk about that today. Soon. I'll give you a preamble for what this is. When we talk about friction, should be today's Tuesday, should be Thursday or Friday. There is and it's something that you guys would have experienced if you've ever pushed something really heavy. It is harder to get a non-moving object sliding than it is to keep it sliding. Have we experienced this before? You're pushing on an object, and once you can get it going, all of a sudden it's less work to keep it going. You just have to keep it moving. And the reason for that, and he falls. There is a concept called static friction and kinetic friction. Friction is different depending on whether or not you have a moving object or not. And we'll talk about why that is, but at this point, it's enough to say that it does exist. And once you break, and I'll go up to here again, 120, oh, dang it, I want that, 120, don't do that. Once you break, so this is static friction. It's not moving. You've got a friction force that's equal to and opposite your applied force. Once you exceed whatever static friction is, then kinetic friction takes over. And kinetic friction is always lower than static friction. We'll talk about why that is in a couple of days. So if you got a chance to play with it, that's what you should have seen. That the force of friction drops once you get the thing moving. Oh yeah, and I've got values here. We placed the 150 kilogram box. How much force is required to move it? Anything bigger than 125 newtons, the thing's going to move. If you put a second block on top of that, your prediction could have been that you needed, because it's a second 50 kilogram block, it's going to be twice as big. And then if you would have tested that, you would have seen that to be true. Anything bigger than double the force would have done it, which is my prediction and my result. The two forces doubled. And then if you wanted to move the refrigerator is 200, which is 4 times the 50. So then I predicted it would be 4 times the 125, and it was. And then if you took a look at the present, the mass, or the present required the same amount of applied force to get moving as the crate did, which means the present had to have the same mass as the crate did. Because they both required 125 newtons, the force maxed out at 125. Anything bigger than 125 got them moving. Because that's true, the two masses had to be the same, the mass of the present and the mass of the crate. So a bit of a preamble into the world of friction. I hope you got a chance to play with that. If you didn't, and I see some of you furiously writing down my stuff, you've got your laptops. I'm sure you have the internet. If you don't have the internet at home, then you can do it here. But that is what something I wanted you guys to play with. So, where were we? My booklet for this unit. Then we went ahead and we looked at forces of gravity. And we start on my last day here, Tuesday last week. We started this one. I wanted the jumping on the moon activity. What kind of verticals did you guys get? Are there any questions here you'd like me to help you with? What were our values for your verticals and your time in the air on the moon and on the sun? What did we get here today? What'd you get for a vertical on the moon? Find this page. 15.2 seconds on the moon. Okay, and your vertical? How'd you get the time then? How'd you get the time then? So let's work it through then. You had an initial velocity for the Earth. Okay, what was your initial velocity for the Earth? 24.2 meters per second. Yeah, that's very quick. What was your vertical on the Earth? 30 centimeters. Okay, so 30 centimeters. We're going to convert that to meters. Would have been 0.3 meters. That's an important first step. Because if you don't convert this thing to centimeters, then when you use kinematics to find your initial velocity, A is going to be negative 9.8. If this is 30 and this is negative 9.8, that means you're telling your equation that you jumped 30 meters. You need your units to line up. So if your vertical was 30 centimeters, that should have been 0.3 meters. So your acceleration would have been negative 9.8 meters per second squared. Your V final, if you want to know your V initial, the one thing we do know is that at the top of your vertical, your VF would have been 0. Because that's how you get to the top. That's how you know you're at the top, is when you stop moving upwards. And now we want to know what VI is. This notation here, V0, is your time at the beginning, V at 0 time, which is what we've been calling VI for the longest time. So we're going to use a kinematic equation, VF equals VI plus AT. VF is 0, VI is what you're looking for. Acceleration is if your vertical is positive 0.3. Oh no, that's the wrong equation. I don't want that equation. VF squared equals VI squared plus 2AD. That's not what we use. So we're going to square that guy. We're going to have 2 times negative 9.8, which is going to be negative 19.6, times 0.3. So 0 is going to equal VI squared minus, what is 19.6 times 0.3? Times 0.3 is 5.88. So we're going to add this over and then square root. So we're going to have the square root of 5.88 equals VI squared. So the square root of 5.88 is 2.42, which tells me you didn't convert from centimeters to meters. Meters per second. So this should have been is what your V0 should have been. You guys should have all had an initial velocity somewhere. I mean, I'm expecting them to be below 4. But this is the procedure. Once you know what your vertical is, you know your final velocity at the top is 0. We know what the acceleration is. We plug it into kinematics and we solve for it. The handout told you guys to assume that this was true all the way through. Obviously, this isn't entirely true. On the moon, you're going to be able to push your mass upwards faster than this. And on the sun, I'd be surprised if you could stand it all. But assuming this is true, calculating these two would have looked like this. Maybe I should have got you guys to hand these things in. Next time I'll make it a quiz or something. Now we've got an initial velocity of 2.42 meters per second. We want to know the maximum height and the time, the hang time, so the total time in the air. So we can use VF equal, we can pick a value in there. The acceleration on the moon is negative 1.6. We want to know D at the top, and we want to know T total. Now, there's 2 ways you can approach these things. To find T total, one of the ways that we could do that was we could say that the V final was the negative of the initial. One of the things that we talked about in projectile motion was that going up and coming back down. As whenever you're level, your speeds are going to be, or the velocities rather, are going to be equal and opposite. Or that we could say your VF is 0, and then T total is going to be 2 times the time to the top. Because again, when the path is level, when you're going up and back down, and you're landing where you left from, the time is going to be, the time to the top and the time to the bottom are going to be the same because your acceleration is constant the whole time. So I'm going to set that up this way. I'm going to say my v final is 0. I'm going to find the time to the top and the displacement at the top. So to find the displacement, we'll just use Vf squared equals Vi squared plus 2AD. And for the time, we're going to use Vf equals Vi plus At. This one's going to be 0 equals 2.42 squared plus 2 times negative 1.6 times d. If you do that, you should find that on the moon, negative that, divided by that, divided by that. So if you went from a 30 centimeter vertical or a 0.3 meter vertical, your vertical should have been 1.8 meters, which means you're jumping somewhere in the neighborhood of your own height. A straight leg jump would put your feet where your head is now, which would be weird and kind of awesome. And then the time for that same jump would have been 2.42 divided by, you should have found somewhere in the neighborhood of 3 seconds. So I think using Hirday's values is a good approximation for all of us. A number around 2 meters and a time around 3 seconds would be reasonable, I think, for most. I had one student a couple years ago, Nick Martino. I don't know if any of you remember who he was. He was a rugby player. Had just an absolute ridiculous vertical. We made him demonstrate it for the class. It was legit. His was the biggest number I've ever seen, and even that, it wasn't much bigger than this. It might have been actually 4. I think. I can't remember totally. But this is the procedure you're walking through. This conversion at the beginning is really important. Do you want me to go through some values, like the sun calculation, just to kind of compare your values? Okay. So this one's going to be similar via I. The only difference here is that this acceleration is going to be negative. Instead of negative 1.6, it's going to be negative 274. The sun's a lot more massive than the moon. The acceleration due to gravity is a lot bigger. So the only difference here is that this acceleration, A, is going to equal negative 274. Otherwise, these calculations are the same. So we're going to get 0 equals 2.42 squared plus 2 times negative 274 times d. And this one's going to be 0 equals 2.42 plus negative 274 times t. And then, of course, we're going to double the time at the end. So for this one, you should have found here today that your jump on the sun you're going to get 0.01069, which is just over a centimeter. So you're jumping this much on the sun. Jumping as hard as you can, you're going this high, which even that's impressive. And your time in the air, well, there's no air on the sun, but you get my meaning. 2.42 divided by 274 times 2. You're in the air for 0.02, I'll see T total here, is 0.02 seconds. So you're jumping just over a centimeter, and you are back on the surface of the sun in 2/100ths of a second. So these are the kinds of values you guys should have been looking at. I don't expect, much bigger than those values. The only difference being the size of the sun produces a much larger acceleration due to gravity. Does that make a little more sense? Okay. Something you guys should be able to do. My video talked about this, yes? You saw this portion of the video? I can't remember. Did you guys see this? Or no? Okay. I can talk about it here. One of the things that pops up in this conversation is this idea of g-forces. So we talked about the force of gravity. The force of gravity is the force created by a massive object on everything interacting with it. If we've heard of, how many of you've heard of this term g-force before? Okay. All it means is that on Earth, a g-force is just a multiplier of this acceleration due to gravity. So there are ways that you can accelerate yourself, driving a car, riding a bike, getting on a plane. You can accelerate yourself at rates either more than or less than the acceleration due to gravity. We say that the acceleration due to gravity is equal to 1g, and then we can use this as a multiplier. So it's related to, so while you're resting on Earth, you right now, sitting in your chair, are experiencing 1g. We put you in a car and we start accelerating you, or we put you in a plane. If a car accelerates at 4.9 meters per second squared, well, because 4.9 divided by 9.8 is 0.5, like this acceleration here is half of the acceleration due to gravity. What that means is in that car, you're experiencing half a g. Now, it might be kind of weird to think about that, but if you think about how you experience the acceleration due to gravity, your body is only used to experiencing it down. And so while you're sitting here, you are experiencing 1g. You're experiencing the acceleration due to gravity while you're being supported. If I push you off the building, or I throw you out of the plane, or however you want to experience falling, you jump off of a swing, you're still only experiencing 1g, but you're experiencing it now unsupported. So now experiencing it unsupported, that feeling of falling is 1g. So now we put you in a car and we accelerate you forwards or backwards. If the car experiences an acceleration of 4.9 meters per second squared, assuming the car is accelerating forward, you're experiencing half a g. The shuttle no longer exists, so perhaps you don't necessarily. Does anyone? We've seen the space shuttle before? Hands up if you know what I'm talking about when I say the space shuttle. Well, that's so sad. Space shuttle was one of the coolest things I thought. Yeah. When I was a kid, I thought it was one of the coolest things. This is the space shuttle. This thing. We've seen pictures of this thing before, I hope. There were, I think there was 5 of them. There might have been 6 of them. And they have been retired. They are now spread at various museums around, well, except for the 2 that exploded. They are now spread around the United States in various museums. This is the Orbiter. You can go down to Seattle and see the training one. It was pretty cool. They lost a couple of these and then have since retired the program. But if you take a look at how what it looks like all suited up here, I'll pick this picture. I want a big picture. Is this picture big enough? Nope. Yeah, these are small. Yeah. Well, I hope you can see it from where you're sitting. This is the Orbiter. You can see that this big white thing is the only thing that actually makes its way back. It had 1, 2, 3 different fuel tanks here, and it was fueled in stages because you need a whole bunch of fuel to push you You need fuel to hold the fuel required to push you to get into space. Getting to space is actually really complicated. And so how this system would work is that these two white outer boosters would ignite first, causing liftoff. And this big orange tank here was yet more fuel. When these guys were done burning, they would detach, and then this guy would detach. And now all of a sudden, you've got this guy now orbiting in space all by itself. This thing was capable of producing an upwards acceleration of 28 meters per second squared. At the time, one of the most if not the most, it was one of the most powerful vehicles on the planet. Can produce an acceleration of 28 meters per second straight up. But even that, though, is only, if you do the math, only 2.86 Gs. So less than 3 Gs. So for those of you who are interested perhaps in aviation, we also talk about stuff like this. So a normal human, you guys, completely untrained with no special equipment, can withstand 4 Gs. Now, so like things like a roller coaster, or we could put you on the shuttle, we could blast you into space and you'd be fine. Now, when we say withstand 4 Gs, more than 4 Gs isn't necessarily going to kill you, but this seems to be the line where most normal people with no special equipment start to lose consciousness. Because your body, when you start to accelerate like this, inertia starts to impact parts of your body that you don't normally expect, or you don't normally think about having their own inertia. So you think back to the car. When you guys are in the car and the car turns the corner, you slam into the side of the car. Yes, we've experienced this. We've talked about this as a class. Now, when we shrink, when we look down at smaller and smaller things, your blood vessels, walls inside your body carrying it's a plasma. It's not quite a liquid, but there's liquid components. There's solid points within your blood as well. You got white blood cells, you got platelets, you got your red blood cells. Now, the only one in there that you require on a day-to-day basis, assuming nothing else is wrong with you, are the red blood cells. Those ones are wildly important. Those of you who have never taken biology before and have never watched a Magic School Bus episode, your red blood cells are how the oxygen that you breathe in makes its way around your body. Now, those things have mass. They're really small. We don't typically think about it. But when you start to accelerate beyond 4 Gs, the mass of those red blood cells causes them, and the rest of the blood, causes them to start to slosh around in your body the same way you slosh around inside a car. So if you're sitting in a seat and you start to accelerate forwards at 4 Gs, the blood wants to stay where it is while the rest of you rushes forward around the blood. Obviously, the back of the walls of your blood vessels are the thing that's going to hold the blood there. You move forward, so does the blood. You're sitting there, it's relatively normal. The blood still gets to circulate. In something like the space shuttle, you're lying there while the thing accelerates upwards. Again, not a huge deal. It was probably one of the most, I said before, one of the most powerful vehicles we had on the planet at the time. Still only produced Gs of 2.86. People can withstand 4. The easiest way to get your acceleration due to gravity up, or your G-force experience up, is to change your velocity. All an acceleration is a change in velocity, by changing the direction you're moving in. That's how roller coasters do it. And when we talk about jet planes or fighter jets, that's what fighters are doing. It's not accelerating in a straight line. That's never the problem. The problem is accelerating in a circle or in a loop, or twisting you, if we can twist you fast enough. If we do a loop, or even if we do a sideways loop, the way a jet does a sideways loop is it turns you on its side and then they pull back and they do the loop. It's not like driving a car. When you do that, you're no longer sitting upright. And your blood is going to start to pool in the lowest parts of you, typically your legs. Past 4 Gs, your blood or your heart, for most people, your heart isn't strong enough to pump your blood back to your head against the pull of gravity on your blood vessels. And so past 4 Gs, you start to lose consciousness because your brain's not getting any oxygen. Now, there's equipment that fighter pilots have that constricts their legs. It's a compression suit. If you ever worn, does anyone have any of you worn compression socks, for example? So my grandma had a pair of these because her circulation was really bad. So what the compression socks will do is they'll hold, they're tight around your legs so that the blood cannot pool in your feet and calves. It pools higher than that in your thighs, and so it's closer to your body. Your heart has an easier time pumping it through the rest of you. Using this special, so a fighter pilot has more than, it's a whole compression suit. It squeezes their entire body so that the blood, the blood from the head is gonna pool anywhere. It's gonna pool at the bottom of the head as opposed to the bottom of your feet. There are also ways you train to compress your muscles. It's a lot of work to sit there and fly a plane because they want to be able to use their own muscles to hold that blood in their head as well. So a normal human, 4 Gs, a fighter pilot, 9 Gs, roughly on average. And from what medicine has told us, anything past 11 Gs will kill a person. So there was I think it was a German engineer, leave it to the Germans to design something as awesome as this, but there was a German engineer who actually designed a roller coaster that was effectively a euthanasia coaster. That one had a bunch of loops, and it was designed so that every loop would hold the riders at would have them endure a G-force higher than 11 Gs, and it would just hold them to that point where they passed out and then eventually went brain dead. It held them at their brain at a state of oxygen deprivation until they just went brain dead. And you would pass out. It would be an entirely painless way to go. It's wildly convoluted. It's effectively a suicide coaster. Not what, you guys have probably not played a roller coaster tycoon, which is really sad. But anything past 11 Gs, your average human is going to die. And so those tight corners are the way to make that happen. So that is a quick aside on G-forces. Just it's language that we've heard, that perhaps you've heard tossed around. That's what it means. They're multipliers of the acceleration due to gravity. And again, we experience these things, the really big ones, while turning, which most of us don't experience on a day-to-day basis. Then I gave you guys a video lesson. On Thursday, I wanted you guys to take a look at the video lesson for Newton's second law. If you weren't here, you're going to have to go and dig in my, not the class YouTube videos, but my old Physics 11 YouTube playlist, and you will find the April 4th video. And it went through this. Now, are there any comments, questions, concerns on anything this lesson covered? It went through FNet equals MA. It looked at how we solve these things. It had you guys drawing some free body diagrams. Is there anything from here any of you would like me to do now that I'm sitting in front of you as opposed to on video? Okay. I'm going to give you a ton of time to respond, so respond quickly if you need to. And then I wanted you guys, there was a bunch of questions I wanted you to play with. This first sheet here, just the first part of it, just had you find the magnitude and direction of the net force. So you're adding forces up. The net force is whatever direction is going to give you your positive force. Again, assuming that you put positive in the direction of the larger forces. So for example, these first chunk should have looked like this. Your first 6 questions should look like this. There's no net force here because in every direction you have balanced forces, 100 up, 100 down, 20 left, 20 right. F net here is 0. So if this object is not moving, it is not going to move. This one's going to have a 250 Newton force up because it's a 400 up and 150 down. So this one minus this one is going to give you the 250. This one's going to be 175 to the right, 60 right, 100 right, 55 left. Is there anything in here anyone wants me to explain in more detail? Compare what you got with what I got. Or, you know, copy down the answers because you didn't do the question. You should have had time. Thursday was a normal length block. I think my video was only half an hour. You should have had almost an hour to do this stuff, the rest of the stuff. And then this one would have looked like this. It was information. It wanted you to fill in the missing values here. They gave you, what did they give you? Different things in each one. Sometimes they gave you the mass. Using the mass, you can find the force of gravity. If the arrows are the same length, the forces need to be equal. There's no other way to do this question other than to assume that these two are equal and that this one is then 0. So it's an extension of the first 6. Is there anything on this page anyone would like me to go over? Talk about in more detail. Yeah, here it is. The fourth one, this guy? Okay. So if I'm looking at that fourth one, there's 160 normal force upwards, which is weird, and a force of gravity downwards we don't know. What we can calculate, because we looked at the force of gravity, we said the force of gravity is equal to Fg is equal to your mass times the gravity field that you're in, or the acceleration due to gravity that you're experiencing. So this is going to be 8 times 9.8. 8 times 9.8 is 78.4. So that's the force due to gravity, and this is the normal force upwards. Now, if you're experiencing this, 160 upwards, 78.4 downwards, that means these two forces are not balanced, and so you're going to have a net force. F net is going to be the 160 up minus the 78.4 down. And that's going to be equal to a mass times an acceleration. Now, we know the mass is 8, but we'll get there. So this is going to be 160 minus 78.4. That's going to be, why my brain is not operating at peak efficiency right now. 160 minus 78.4, 81.6. So 81.6 is your net force. That's going to be equal to your mass, the 8 kilograms, or the not your mass, but the mass that you're given, times the acceleration. Now we're looking for the acceleration, so 81.6 divided by 8. It's going to be just over 10. In fact, it's going to be 10.2 meters per second squared. Comments, questions, concerns. Does that make sense here, Day? Is that procedure? And so that how you found that, or how you solve that, is going to be true for all of these. This one down, the fifth one here, gives you the acceleration. So you're going to have 200 minus your force of friction is going to be equal to your mass times your acceleration. So it's going to be 200 minus the force of friction is going to equal the 40 times 4. So 200 minus your force of friction is going to equal 160. And now you're solving this thing for the force of friction. I'm going to subtract over the 200. We're going to get the negative force of friction is going to be equal to negative 40. So that means your force of friction is going to equal 40. For example. Anything anyone wants me to go through here in more detail? This is what you're looking for. That's what you need to be able to do. Okay. Hearing nothing, seeing nothing. Was Vine here Wednesday, Thursday last week? Both of them? Okay. This is what I wanted you guys to do on this page. Do odds here. I hope you saw that. These are the answers that I wanted Mr. Whitman to toss up on the screen. See, some of you have them written down, so that's great. Is there any of those odd questions anyone wants me to do? 1, 3, 5, 7, 9. Do number 1, you betcha. Okay, so question 1 says that you've got a car accelerating from rest to 60 kilometers per hour over a distance of 45 meters. So, we've got a car. We've got an FG, we've got an FN, we've got, all we're told, we want to find the F net. There's going to be a force backwards. It'll be drag on the car. We don't need to, it's not asking for what the applied force is. It's not giving us enough information for that. What we want to find is this net force here. Well, your F net, according to Newton's second law, is equal to your mass times your acceleration. So the F net on the car is going to equal the 1100 times A. Well, we don't know what A is, but we're given enough information to find it using kinematics. We know that VI is equal to 0. VF is equal to 60 kilometers per hour. The displacement during that time is 45 meters. We want to know what the acceleration is. A huge part of what we discussed in kinematics is making sure your units line up. So if this is kilometers per hour and this is meters, when we were looking at accelerations, I tried to make a big push that you guys do not want to find accelerations in kilometers and hours squared. Don't do that. The numbers are going to be ridiculous. So I'm going to convert this thing into meters per second. To convert kilometers per hour into meters per second, it's going to involve this number 3.6. Am I multiplying or dividing by 3.6 to put this thing into meters per second? You are dividing. So 60 divided by 3.6 is going to be 16.6 repeating. So we're going to call that 16.7. And now we can use kinematics to solve this. We're going to VF squared equals VI squared plus 2AD. 16.7 squared equals, VI is 0, so that's gone. 2 times A times 45 meters. So 2 times 45, that's just 90. So we're going to 16.7 squared is going to equal 90A. So your acceleration is just going to be this 16.7 squared over 90. That value is divided by 90. I got 3.1. So pretty impressive for a car. I think. So then to find the net force on the car, you're looking at 1100 times the 3.1 we just found. You're looking for a net force of 3,401. Nope, 410. If we take a look, please let there be a 3,410. There it is. All these answers are given to the correct, if you remember back. We had a discussion on sig figs, and while we were looking at sig figs, I did discuss that. We would look at, like, the answers that I would give you would be to the correct number of sig figs, which gives you guys room for a little bit of rounding. So those are, there's that. Diego, does that make sense? Yeah. Okay. Anything else anyone wants me to go over 1 to 9? Okay. Is there anything else anyone wants me to go over on this page? I wanted you guys to take a look at all of these as well. These ones had the answers connected to them. Is there anything anyone would like me to do? Okay. Oh yes, I can do 5. Let's do it. So a 1,200 kilogram bovine, so a cow. That's all that is. 1,200 kilogram cow accelerates uniformly. Why? I don't know. From a speed of 5 meters per second to 12 meters per second. During this acceleration, it travels 94 meters. What is the magnitude of the net force acting on the cow? This is similar to the one we just did. We've got a cow. We want to know what F net is on the cow. And so we know the mass of the cow is 1,200. We need to find the acceleration. F net equals ma. We know the mass. We need to find the acceleration. We're given an initial velocity and a final velocity. So vi is 5. Vf is 12. We want to find the acceleration. And we know that it does it over 94 meters. So Vf squared equals Vi squared plus 2AD. Vf is 12, so 12 squared is 144 equals 25 plus, that's 188. So you're going to get an acceleration of 0.6. And then 0.6 times 1,200 is going to be 760. Well, 0.6 times 1,200 is actually going to be 720, but you're close enough. If I hadn't rounded this quite so aggressively, you'd get 760. So similar to the first question on the previous page. And that's everything you guys would have done Wednesday, Thursday. Questions, comments, concerns on any of it? Okay, then let's take a look at something new. Find me this page here, Newton's third law. So Newton's first law is your law on unbalanced forces, or the law of inertia. The second one is F net equals ma. And this one is one that you've, again, almost certainly heard of peripherally in pop culture. Newton's third law, everyone loves to quote this one. What's the law we haven't heard yet? Yep. Almost. For every action, there is an equal and opposite reaction. Now, this gets used and abused all the time. It's not like, you're hanging out with your sibling. You punch them, so they come up and punch you back. That's not what we mean here. What Newton meant by this is that every interaction involves two forces that we're going to call action-reaction forces. And these pairs of forces always act on both objects. So if you think about the example that I just said with you and your sibling, when you punch your sibling, hands up if you ever punched someone. I'm not going to ask you what the context was. I just want to know whether or not you've actually hit somebody. I have punched someone. I have lots of male cousins. I have a younger sister. Punching happened. It's not a pleasant experience. Punching someone, again, there's a reason why you want to have good form when you're punching. I have seen people make a fist like this. The thumb goes in, they do this. If you punch someone like this, what's going to happen to you? The thumb's going to break. You're going to break yourself right here. Why? Here, Dan. Yeah, because when you punch them, whatever part of you that you hit pushes back on you in that moment. It's not like I punch you, so you punch me back. You have already punched me back. Me punching you, whatever force I exert on you is being exerted back on me. So people who make fists like this are going to break a finger, their thumb. So you make a fist properly when you punch. Because the reason, and we do still punch because, well, the idea being that if you prepare yourself properly, yes, the forces are going to be equal, but you're punching someone where they're not necessarily either ready for it, or it's a part of the body that is going to respond in them like your thumb would if you punch like this. Which is why if you've ever punched someone in the head, I hope you haven't, because that crosses the line, it's actually really painful to you, not to them. If you punch someone in the head, this is not a very squishy object. In most people, this isn't very squishy. There's not a lot of space between the skull and the outside of you. Punching someone, yes, you can break their jaw, you can break bones in the face, but you're also going to break your hand in the process. The head is a very hard object. So punching someone in that, because when you punch, whatever you hit pushes back on you with whatever force you put on it. So other examples, you hit a baseball with a bat. You have the bat hitting the ball. That is one part of it. But if the bat is applying a force to the ball, that also means the ball hits the bat. It means the ball also applies a force on the bat. Hands up if you've ever hit a ball with a bat. And if you've done this, like with someone pitching it at you, or just sitting there on a tee. Hands up if you've hit a ball pitched at you. Okay, good. Lots of you. That's great. When you swing a bat at a pitched ball, what does it feel like? What happens to the ball? Or what happens to the bat in your hands? Sorry, Adafa? You can feel a little bit of back push, perhaps. Yeah, what else happens here today? Yeah. Another way to think of, another way to experience it, if it's been a bit of, if you've experienced it with a pretty effective pitcher, the ball's probably moving fairly quickly. You'll feel the bat vibrate in your hands. It actually hurts. If you're not holding onto the bat properly, it's going to vibrate in your hands. That's why batters wear gloves. That's why learning how to hit, it's important to hold the bat tightly, because it's not just you hitting the ball, it's the ball hitting the bat. That happens together. We don't necessarily think about that because if you ever watch baseball, one of them, you can see the effect on the ball. The ball flies out to the other. It was going at you, now it's going the other way. We don't see the effect on the bat, the vibration in the batter's hands, because of the mass difference between these two. So the bat mass is typically much greater than the ball's mass. It's also not just mass, it's the fact that the bat is tied to who's ever wielding the bat. You're holding on to it. It's not going to fly away. It moves like, or if you've ever watched baseball, the bat moves through the space that the ball occupied like there was nothing there. But that doesn't mean there was no effect. The same way we talked about walking before. How do you actually walk? Well, forget a sprinter. Let's talk about you. How do you run? Well, you push back on the ground. How do you move forward? If you're pushing backwards, how do you move forwards? Well, the ground must be then pushing on you just as hard. It's easier for you to move through the air than it is for you to spin the earth the other way. So because the air has next to no resistance on you, and the earth is going to fight you making it spin based on its inertia, you go forward, the earth does not go backwards. So you push on the ground, or you push on the ground. As you push on the ground pushes back on you. You have less mass than the ground. So you move forward, the ground stays still. It's all about inertia again. Or a fish swimming through water. To move forward in the water, the fish pushes on the water. And the water pushes back on the fish. Everything exists in one of these action-reaction pairs. So let's make it a little bit more extreme. Let's imagine a bug hitting the windshield of a semi-trailer. What force pair occurs? Well, it's an extension of all these questions, right? The bug hits the windshield. This one's dead. The bug hits the windshield. There should be an L in there. Windshield. And at the same time that the bug is hitting the windshield also hits the bug. Which of those two forces is bigger? That's a trick question. Newton's third law says, for every action, there is an equal and opposite reaction. So which of those forces is bigger? Yes, the bug is going to die. Yes, we've established, yes, your life experience tells you the bug will die. But physics tells you that, here today, it's a trick question. They have to be equal. The forces are equal. But why does the bug experience it so much worse? Which force is bigger? Neither of them. If the bug hits the windshield and the windshield hits the bug, that is an action-reaction pair. For every action, there is an equal and opposite reaction. They have to be the same. Why does the bug experience things so much more aggressively than the truck does? Well, let's take a look at this. Let's look at their accelerations, shall we? So we're going to set up something that looks like this. I need more space, some space for this. We'll have F net equals ma. Now, the forces are equal and the forces are opposite. So the force on the bug has to be equal to the force on the windshield. So the force on the bug is going to be the mass of the bug times the acceleration on the bug. That's going to equal the mass of the truck times the acceleration of the truck. Now the mass of a bug, I googled just a generic bug. We're gonna put a value in here of 0.000025 kilograms. Just to put that into perspective. That's 0.25 grams. Very small insect, perhaps a mosquito. Because if you're going to kill a bug, it may as well be a mosquito. And let's find the mass of a truck. Now, I used to work at VersaCold. VersaCold doesn't really exist anymore, but VersaCold was a cold storage facility. I would load these semi-trailers all the time. So we're going to give the mass of the truck, I figured, 36,288 kilograms. Because when we load these things, I'd load them in pounds. This is a value I know to be relatively close to true. Obviously, it's going to change depending on how much fuel's in the cab and all that jazz. But a fully loaded semi-trailer is going to be around this many kilograms. Now, the impact acceleration of the truck. Both of these objects, because they're experiencing a force, they're going to experience an acceleration. Now, the acceleration of the truck is going to be minimal, but it's still going to be there. Hands up if you've ever taken a ferry from here to Vancouver. Okay, those of you who put your hand up, hands up if you went and ran around outside while the boat was moving on the ocean. Yes, you never did. Lena, here today, you did. What did you experience? It is weird. Why do you experience? Sorry? I can't hear you, man. Okay. If you're running around in the wind, what did you experience, Lena? With the wind. Sorry, against the wind. Into the wind. Going. Let's run with the boat. Like you're running up from the back to the front as the boat is traveling forward. Oh. It's not about the fastness of the ferry, it's about the speed of the wind on the ocean. Okay, so if you're going on a calm day, fair enough. If you've never experienced this, that's really sad. When you can get yourself on a ferry on a windy day on the ocean, you can get yourself to the point where you can stand still and lean forward. Now, standing here, leaning forward, I can't lean very far before I start to fall forward, yeah? You can lean pretty far forward on a ferry because the wind holds you up on a windy day on the ocean. The wind's going to hold you back. And if you think about what wind is just the rapid movement of teeny tiny molecules of whatever the air particles are, oxygen, CO2, whatever pollution's there, nitrogen gas, all that kind of stuff. But if the wind is able to hold you up and then possibly push you back, and wind is just a whole bunch of microscopic objects, a bug, a single bug, much larger than a molecule of air, is going to be able to likewise produce an acceleration on the truck. It's a single impact, not millions of impacts, but the concept is the same. If a million small impacts are able to cause you to experience a force that'll hold you up against gravity or push you backwards, a single bug's going to be able to impact the acceleration of a truck. So I'm going to give it a value. Small value, relatively small value. We're going to assume that the acceleration on the truck is just 0.1 meters per second squared. Now, it's probably larger. That number is probably larger than it actually is, but if that's true, let's look at the acceleration on the bug. If this is 0.1, the acceleration then on the bug is going to equal 36,288 times 0.1. And now to solve for the acceleration on the bug, we're going to divide by the mass of the bug to isolate for a bug. So I'm going to take this, I'm going to divide by the mass of a mosquito, which was 0.25 grams, 0.0000025. If you do this math, you are going to find that the acceleration of the bug is 145,152,000 meters per second squared. So the forces on the bug and the force on the windshield are equal and opposite. So why does the bug explode and the truck hardly feels anything? Comes back to inertia again. The larger the mass, the smaller the acceleration that mass is going to experience because it has more inertia. So the truck feels hardly any change to its velocity. The bug has an acceleration of 145,152,000 meters per second squared. The bug is vaporized effectively. All of these have action-reaction pairs, and that's all. Today's lesson, today's homework, there's not going to be a lot of calculation there. It's just going to be an exercise in you labeling some of these forces. So recoil, if you've never shot a gun, you shoot the gun shoots you back. Why? What happens in there? Forget the water pistol, make it an actual gun. In the chamber here, you've got a small object, a bullet. Maybe that's a big bullet. And in that bullet, you've got a whole bunch of gunpowder. There's a primer on the back of that thing. Hammer in the gun hits that primer and ignites the gunpowder inside the gun. When the explosion here occurs, you get this action-reaction pair. You get a force on the bullet, and you get a force on the gun. Now, the mass difference, and these are equal and opposite. The reason you don't die when you pull the trigger on a gun is because the mass of the gun means that even though these two forces are equal, you don't experience the same kind of acceleration the bullet does. The bullet is much smaller. It goes forward. The gun slams into you, whether it's your wrist, depending on how you're holding your gun, the wrist or your shoulder. But the gun is massive enough that it doesn't accelerate at the same rate, even though experiences the same force. I wanted Vian to be here because I wanted to ask him about this. But breaking bricks is exactly the same idea. Your hand hits the rock, and the brick hits your hand. Equal and opposite. And a rocket is similar. A rocket isn't pushing on the air. Just like in the gun, there's an explosion going on in here constantly. Fuel is being burnt and exploding. You get a force this way and a force this way. You get gas pushing on a rocket. And you get a rocket pushing on the gas. Sometimes I'll have students will suggest that, well, in the atmosphere, this ejecting gas is actually pushing on the atmosphere. That's not true. If that were true, a rocket wouldn't work in space. The rocket is pushing on the explosion that's happening inside the rocket, which causes the gas to get ejected out the back and the rocket to move forward. So this today is all about just identifying these action-reaction pairs. So I know there's not a lot of time left, and it's actually not a bad lesson to do with having been away for a couple of days. All I want you to do is identify the action-reaction pairs on this page and the next. You could theoretically get this done in the time that remains. Welcome to Newton's third law.